All right, in this video I'm going to talk about section 5.2, which is mostly about definite integrals. But the most important part about this section, I believe, is evaluating a definite integral using the limit of a Riemann sum. So I'm going to do a few of those examples and then one extra example about finding the integral using a graphical argument. So first off, let's say we want to evaluate the area under the curve 4x cubed between 0 and 2. So here, if you think about this in the language of a Riemann sum, right, the function that we want is 4x cubed, right, on the interval of interest 0 to 2. So if I want to evaluate this thing using the limit of a Riemann sum, I first have to construct that Riemann sum. So that means finding delta x, which is b minus a over n, which is 2 minus 0 over n, which is 2 over n. So the main difference here between this section and the previous one is that n is not specified, right? So we go about the Riemann sum business, right, just assuming that we know what n is. So n could be any number of rectangles. So we leave n in our expression. But one thing to notice is that, right, n is fixed. So it's some fixed number. Okay, continuing on, then we can find, again, xk star, which is defined as a plus k delta x. So in this case, that would be 0 plus k times 2 over n. And so we get 2k over n. So that's the form of the right endpoint. And so r sub n, the right-hand Riemann sum with n subintervals, would be defined as k equals 1 to n, right, of f of xk star times delta x. So we have to go through now and essentially simplify this thing. So f of xk star, that would be f of 2k over n, right, times delta x, which is 2 over n. So we get k equals 1 to n. Now apply f to the term 2k over n. That gives me 4 and 2k over n cubed times 2 over n. Now let's simplify the summand. So this would be 4 times 8k cubed over n cubed times 2 over n. Simplifying even further, we would get 32 times 2, right? So that would be 64 k cubed over n to the 4th. Now, since n is a fixed number, it's a constant, it doesn't depend on k, and 64 doesn't depend on k, I can factor both of them out. So now we have just the sum of k equals 1 to n of k cubed. And here's where we can use the identity. Okay, so the sum from k equals 1 to n of k cubed, there's an identity for that. It's n to the 4th over 4 plus n cubed over 2 plus n squared over 4. And so simplifying this, we get, I'm going to multiply this in, see how I would get 64n to the 4th over 4n to the 4th, plus 64n cubed over 2n to the 4th, plus 64n squared over 4n to the 4th. So this cancels the 64 and the 4 and the n to the 4ths, so we get 16 plus 64 and 2, that cancels, leaving me with a 32 over n plus 16 over n squared. So this is my form for the Riemann sum with n subintervals. Now, this is really nice because, look, there's an n on the bottom here and an n squared on the bottom. So as n goes to infinity, these two terms will go to 0. So that is the actual definition of the true area. So the area between 0 and 2 of 4x squared dx is the limit as n goes to infinity of r sub n. So that would just be the limit as n goes to infinity of 16 plus 32 over n plus 16 over n squared. And we've done limits like this before, right? As the bottom blows up, this will be like 32 over infinity, which is a really small number. It goes to 0, goes to 0. So we're left with exactly 16. So the area under this curve, 4x cubed between 0 and 2, right, is equal to 16. This will always kind of happen when you do this Riemann sum, right? You should get only terms that have an n in it should be in the denominator because they will go away. Let's do one that doesn't start at 0, right? It starts at 1. This is a little bit more confusing. So here again, my function is x squared minus 1, and my interval is 1 to 4. So I find delta x as b minus a over n. So it would be 4 minus 1 over n, which is just 3 over n. Now I find my right-hand endpoint, which is a plus k delta x. So this would be 1 plus k times 3 over n. So this is 1 plus 3k over n. Now this is going to be harder because I'm going to have to square this number, right? So I'm going to get more terms out, but that's fine. Now the r sub n, that would be the sum from k equals 1 to n of f of x k star times delta x. So this would be the sum from k equals 1 to n of f of 1 plus 3k over n, right, times 3 over n. Now the goal here is to just simplify this thing after we apply f. So this would be 1 plus 3k over n squared minus 1 times 3 over n. Now unfortunately I got to square that thing out. So that would be 1 plus 6k over n plus 9k squared over n squared minus 1 times 3 over n. We see that these two 1's cancel. Now I'm going to multiply this 3n inside as well to save me some time. So this would be 18k over n squared plus 27k squared over n cubed. Split the sum. So this would be 18k over n squared plus the sum of 27k squared over n cubed. I'll bring this up here. So we get factor out anything that doesn't depend on k. So I'll get 18 over n squared times the sum of k equals 1 to n, plus 27, so that would be 27 over n cubed times the sum of k squared. Now is when I use the identities, right? So this would be the sum from k equals 1 to n of k is just n squared over 2 plus n over 2. This would be plus 27 over n cubed, and this one's a little bit more complicated. It's n cubed over 3 plus n squared over 2 plus n over 6. Multiplying inside, notice that I will get 9 because the n squareds will cancel. 18 cancels with the 2, and then plus 9 over n for those two terms. This one I would get 9 again because the 27 and the 3 cancel and the n cubes cancel. Then I would get plus 27 over 2n because the n squared and the n cubed cancel, leaving an n in the bottom. And finally 27 over 6n squared. Simplifying, we get 18, adding these two together. And you know what? I don't even care. This would be 9. I don't even care what the other terms are because they all have an n in the bottom. I don't even care if they cancel. So Rn is considered to be this thing. Okay, so the integral then of 1 to 4 of x squared minus 1 dx, that's the limit as n goes to infinity of Rn. So I look up here and I see that as n goes to infinity, this term will go to 0, this term will go to 0, this term will go to 0. Why? Because they all have an n in the denominator. The denominator is blowing up, so that gets very, very small. So my answer is 18. Okay, so that's another way to do the integral, a definite integral, using the limit of a Riemann sum. The last question I want to look at is something that's kind of crazy. So here, if I try to do this with a Riemann sum, right, I'm not going to be able to do it just because it has a square root and there's no identity for a Riemann sum, right, that involves a square root, or at least one that we're not going to consider in this class. So, but we can actually just draw a picture of what this function is, and it turns out that this is a well-known shape that we should know the area of. So think about this function here. I'll label it y equals the square root of 16 minus x squared. And look at this, for all values of x, right, where this thing is defined, y is always positive. So if I would square both sides, I would get this. And then if I would add the x over, I see that I get the equation, right, x squared plus y squared equals 16. And this is a circle, right, of radius r equals 4, centered, right, at the origin. So I can actually just draw this picture, right? It's a circle of radius 4, centered at the origin. However, remember I had the positive square root. So this is actually only the top part of this circle. Correct? So that's what this function is. So this red function here would be f of x equals the square root of 16 minus x squared. The bottom part of the circle, that's where that negative square root would come in. So if it would have been negative square root, so this function is negative square root of 16 minus x squared. Right? So let's try to interpret what this area means. Well, I'm going from 0 to 4, so that would be the interval from here to here, right, under this graph. So the area that is represented by that integral would only be this, right, quadrant of that circle. So that is exactly equal to that notation. Well, we know how to find the area of the circle. So the area of entire circle, right, is pi r squared. So the entire would be pi times 4 squared. So the entire circle is 16 pi. But this is only a quarter of it. So I'd just take 1/4 of 16 pi. So the answer is 4 pi. So the integral from 0 to 4 of the square root of 16 minus x squared, crazily enough, it's equal to 4 pi. Simply because it's a circle. Okay.